Hello and welcome to Scalable CTO. I'm Bob Dickinson. Today we're talking about AI, what it is, how it works, how we use it, and the APIs and tooling that we built for TeamSpark. So let's get right into it. So the plan today is a controlled dive from 40,000 feet to bare metal. We're going to start very high level, talking about AI and LLMs. We're going to move through some more details and then get into the implementation of how we use LLMs, a strategy that we've adopted called prompts as code, and then we'll get into our prompt engineering APIs and tooling and do a demo at the end. There'll definitely be some coding toward the bottom of this thing, so hopefully that'll be interesting. So let's talk about AI in general first. AI has been around for at least a couple of decades in products you use every day. So things like product recommendations from Amazon or movie recommendations from Netflix or apps like Shazam that can identify a song playing on the radio or apps that can identify birds based on their song or plants based on photographs. Lots of applications around cybersecurity, fraud detection, things that you use every day. And you may not know that those are AI. And even within the community, we largely refer to those as machine learning. AI is the broad term for kind of any technology that enables computers to simulate human learning, comprehension, and problem solving. And machine learning is sort of the biggest part of that. And you can see from this diagram on the right, kind of visualization of that. It's probably worth pointing out there's not really a shared model for all the pieces of AI and how they fit together. There's lots of different diagrams like this. I particularly like this one, but there's a lot of other ways of looking at it that kind of relate things like natural language processing and neural networks and all the pieces that make up some of these things. But I think this does a good job of showing a couple of things. First of all, that really most of what we use day to day and most of the things we're still thinking are exciting, things like robots and self-driving cars are really around machine learning. And they're sort of separate from generative AI, which is one particular slice of the deep learning, machine learning pie. So generative AI has gotten a lot of attention lately with ChatGPT, particularly in the follow-on products. Generative AI is an implementation of machine learning that is oriented around creating new content, generating new content, which is the generative part of generative AI. Typically by learning from a large corpus of data of that kind of content and then using prompts to drive creation of new similar content. So GenAI is really just one piece of of machine learning, which is just part of AI, but it is the part that's getting a lot of press and a lot of excitement and a lot of investment right now, and it's the part that we're using in our product. So that's what we'll primarily be talking about today. So within GenAI, you really have a couple of groups. I mean, you could probably divide it into more than a couple, but for our purposes, we have large language models. So these are things like ChatGPT, Claude, Gemini, Copilot, probably the products that you've seen and use mostly, where you can type a question or an instruction in and it'll give you back some generated content. And it'll probably blow your mind in the process. So these are applications of neural networking to human language processing or natural language processing, NLP. They're trained on a huge corpus of language. They take language as their input generally, and they produce language as their output, which is why they're called language models. There are other Gen AI technologies that are around things that aren't so focused on language. They do things like image generation, video generation, music generation, anomaly detection, data augmentation, lots of other applications of things that are Gen AI, but they're not large language models. So just to make that distinction, we're going to talk primarily about large language models. So I want to talk briefly about the Gen AI hype cycle. This is the Gartner hype cycle for generative AI. There's a Gartner hype cycle for everything, and everything kind of goes through this same cycle. The amplitude and the frequency is a little bit different for different technologies and different product categories, but they all go through the same sort of thing, which is that there is this big bunch of hype, this peak of inflated expectations where everybody gets super excited about the promise of some new technology. A lot of very optimistic founders make huge promises and probably overpromise. A lot of investors get a little bit sideways and are so excited that they're investing in things maybe they wouldn't invest in normally if they were being a little more careful. And so what happens is you sort of get these bubbles. You get these bubbles where a lot of people are trying to ride this wave. A lot of people are raising money at valuations that don't seem like they make sense, and they're spending money in ways that don't seem like they're going to have return on their investment. But there's so much expectation around the potential upside of the technology that it just sort of happens. And then at some point, everybody realizes that's happening, and then you get this trough of disillusionment, the trough. And that's sort of the bubble popping when people talk about the bubble popping. It's not really a bubble popping. It's a pretty predictable thing that happens with every technology. And the vast majority of them recover, and they end up becoming products that are more mainstream, that actually start to generate real customer value. They generate real value for the companies that create them and bring them to market, for investors. And all of that stuff really happens on the right side of this diagram. The left side is exciting. Lots of money gets invested. Lots of money gets spent. It's sort of questionable how much benefit gets delivered to users. No profit is made. No profits are returned to investors in this phase. All these people raising these hyperinflated rounds aren't cashing those checks and taking that money home. They're spending it on these companies to try to get them to the other side of this trough. But when you get to the right side, that's when you have bigger, more mature companies, more stable companies, people sort of in it for the long run. A lot of the people who are here just to ride the wave get kind of washed out by this. And this is where really all the value gets created for customers and investors. So unless you're a founder whose startup is an AI startup, not a product that uses AI to deliver value, but where AI is the product, you're going to be fine. Those kind of founders are great here. They're going to sort of do terrible here. Maybe even some really legitimate founders of some good businesses aren't going to be able to raise money because of the overcorrection. But for the rest of us who are just trying to sort of use AI in our applications, find ways to make our products better for our customers, it doesn't really have much impact on us. So how do we think about large language models? I'm going to show you this video that I made of the predictive text on the iPhone. And I typed a couple characters, and then I'm just sort of tapping on a word sort of at random, generally the middle one, to form a sentence here. And what this predictive text is doing is it's looking at the words that have been typed in the text box before, up to that point, and it's coming up with a word that makes sense in the context of those words to make a valid sentence. It's not looking at any of the other context of the chat session. It doesn't know anything about you or who you are or what words or phrases you use frequently. It's sort of dumb. It's just looking at what are the words that have been typed already and what would be a possible word that would be a next word that would form a valid sentence. And the reason I give this example is because this is not a large language model, but this is a good way to think about how large language models work. They're just models that are able to predict the next most likely word based on the words that came before it. This stuff that you see on the screen here that's been typed, that's what we consider the context. So that's the set of words or tokens for which it will try to continue predicting the next word or token. And what we can imagine is just making this massively, massively better, training it on massively more data, making the models much more sophisticated, throwing a lot more compute at this, and coming up with a model that takes all the information in the world and is able to predict the next most likely word based on some words that you've given it. And it's kind of amazing, and we'll talk about all the things that result from these models and the things that they can do. And it's pretty amazing that they can do those things given that this is how they work, but this is how they work. They take a huge model that allows them to predict the next most likely word based on some context, and then you give it a prompt or some data and it does that, and that's sort of it. So let's talk about some properties of LLMs. The first property I want to talk about is that LLMs create bullshit. And bullshit's sort of intentionally kind of a catchy headline there. This is from a paper called ChatGPT is Bullshit from the people at University of Glasgow. I'll show that in a second. But really, the thing to understand is that LLMs are trained on massive amounts of text. So every web page, every PDF on the internet, every research paper, every Reddit post, the caption of every video on YouTube, every line of code in GitHub that's in open source, like everything. It's trained on the whole internet. Probably not legally. Like a lot of our industries, it starts out very, very fast and loose with the law. But it pulls all this data in and builds this massively giant model. This is the large part of large language models. And the goal of these models is to produce text as a continuation of a prompt that's consistent with the training data. So it's essentially trying to produce text that's consistent with all the stuff that it learned. So given a set of words, what are the next most likely words to follow that, given all of the data that I've been trained on? So these models don't know facts, they don't have knowledge, they don't understand truth and falsehood. They just know how to predict the next most likely word. And so what people that are in this field call that is hallucination. They say that the models hallucinate, but that's not a technically accurate term, and it's inaccurate in a way that causes, I think, people to misunderstand how these models work. And the argument that they make in the paper is that by treating these things as bullshit, which is a topic from philosophy, and essentially understanding that the goal of this model is to create a compelling story, not necessarily to tell the truth, that it helps you understand how to interact with these models better. The hallucination is a human perceptive condition that doesn't really apply to these models. And so I'll show you this paper just really briefly. They refer to the work of Harry Frankfurt, who was a professor of philosophy at Princeton, who kind of pioneered this concept of bullshit, starting in the mid-'80s and culminating in a paper in 2005 that was super popular. Anyway, this is a great rat hole to go down. It's like a 10-minute read, but I thought it was super interesting. So another property of LLMs is that they have emergent behaviors, that they do things that we didn't predict they'd be able to do and we didn't design them to do. And they're surprising and impressive. They're great at summarization, at extracting information out of a body of text. They're good at sentiment analysis, understanding if something's positive or negative, if it's optimistic or pessimistic, classification in general. They're good at language translation. They're good at the newest models are as good as the best human language translators in most cases. They're pretty good at creative writing, generating poems, lyrics, scripts, all kinds of creative writing output. They can parse and generate data in a wide variety of formats. So they've been trained on a lot of data, especially computer code. So they can do things like read CSV files, JSON files, Markdown files, because they've been trained on, for one thing, a lot of source code from GitHub and other kinds of source code repositories. So they can both understand these file formats and also create these file formats in their answers. They can write code, which is pretty surprising and impressive, just based on being trained on lots of source code and lots of articles talking about source code and referring to examples of source code. They have enough power in these models to actually produce source code to solve problems. They're not at the level of a senior engineer, but as probably more like a junior engineer, maybe intermediate at best. Not great at solving super complex problems, not really great at architecture, but in terms of just sort of doing rote, I need a function that does X. They're a huge time saver and surprisingly good. And tool usage is another emergent behavior that we've started to see lately in the last year or two, where you can express to a large language model that it has access to a tool that it can use to answer a question or solve a problem, and it's able to figure out how to use those tools in its apparent reasoning to solve more complex problems. The last property I want to talk about is that LLMs are expensive. And this is not going to be an apples-to-apples comparison, and you might argue that it's not really fair to compare the sort of magic rocket science of making these great human-like predictions to something like accessing data in a database. But I think it's still sort of worth considering, and let's come up with as close to an apples-to-apples as we can get just to understand the scale. So I've taken a sample operation where we're going to read 10 comments on a post, and then we're going to submit one comment and reply to that. So on the database side, that's going to use Google Cloud Firestore. We're going to do a multi-index search on an arbitrarily large database. So this could be billions of records. And we're going to produce 10 results. And then we're going to read those 10 records that are, let's say, the 300 bytes each. And we're going to write one 300 byte record in response. So that's a pretty normal sort of operation that you might do in a social networking application or any other kind of application. And if we did that 100,000 times a day for a month, that would be $25. So these are things that are pretty commodity priced. These are things that are highly scaled and commodity priced. And like most things in this kind of system design, you don't usually really have to worry about the cost of things unless you're doing something really, really extreme. Huge data sets are super frequent. But if you're doing operations in response to end user activity, for example, you can almost not worry about the cost of most of these kinds of operations. And if we go over to the LLM side, we're going to look at a prompt evaluation, a pretty straightforward one. So we're going to use Vertex AI, the Gemini 1.5 model, which is the most current one. And we're going to summarize this. We're going to take those same 10 comments that we read that were 300 bytes each, and we're going to summarize them. So we're just going to give it a simple prompt We're going to submit this prompt of about 3,000 tokens. So it'll be the 10 comments plus the prompt itself. And then we're going to limit its output to 300 tokens, a fairly brief response. If we did that 100,000 times a day for a month, that would be $945. So that's about a 40x, a couple of orders of magnitude increase. Now, if you're not doing these things super frequently, if you're doing them in an interactive chat session on a paid for service or something that you're doing, a few times a day or something like that, you probably don't need to worry about cost. But if it's something you're doing very frequently, the cost may add up. You might be surprised. So you really do kind of need to think about it in your design. And in particular, if you're using large context windows, if you're uploading an entire code base to have a bug fixed, and you're doing that dozens of times a day, you could easily start getting into, tens or hundreds of dollars per user per month, if you're not careful. So I would say, generally speaking, if you are kind of good at system architecture and understand how to use these tools at scale, you almost don't need to worry about the left side of the equation. But this right side around prompt evaluation, you need to at least think about that. You need to at least understand how big are my context windows, what's the pricing model of the service I'm using, how often am I going to do these things, and am I really going to be able to afford that? The other thing about this that's sort of interesting is that we don't actually know if this $945 number is right, because the companies selling these products aren't making money selling them yet. And we also don't know to what extent Moore's Law is going to kick in and those prices are going to go down. So honestly, I think there's as much upward pressure because we're not making money as there is downward pressure because of Moore's Law. So I don't really know. It could just go sideways for a long time, or it could go up or go down by an order of magnitude. But right now, it costs us something to think about. They are expensive compared to other kinds of compute operations. So let's talk about prompt engineering. I guess the number one thing on this slide is I put engineering in quotes. I'm personally a little bit skeptical that the field we call prompt engineering is actually engineering. I think it's sort of prompt science, I guess. I think it's more around discovery and trial and error than it is around what I would consider to be engineering, which is more sort of creation and construction. So prompt engineering is the art of crafting effective inputs to guide the large language models toward desired outputs. So we're sort of trying to trick the model into giving us the kinds of answers we want to the questions that we asked it. In order to do prompt engineering well, you need to really understand the models, their strengths and weaknesses, and they're all different from each other. And you need to understand effective prompting techniques, which are continually evolving, in order to get the best prompts that are going to maximize the potential of your language model. And so just as an example, anybody who's used ChatGPT or any product like that to type a prompt in to generate some content or ask a question probably understands this, but this simple example, explain the concept of prompt engineering to a high school student, keep the explanation short, only a few sentences. So example of a fairly simple prompt that I would give to a language model. So there are a lot of prompt engineering techniques. There's a whole sort of science around that and a whole area of study around that. We're continually discovering new prompt engineering techniques. Those are then researched. There's a lot of academic research in this area and sort of proven out and brought to practice. As a resource, I really like this prompt engineering guide. I'll go here and just give you a brief overview of that. I would start here before taking a class, for example. I like being able to kind of read through, see examples, see videos. If you want to do this like a class, this is organized in a way that at the bottom of every page, there's a link to the next page, and it'll literally take you through the entire website, a page at a time, beginning to end. One of the other things I like about it is that it'll have some videos. As it describes the concepts, it's going to link to the academic research. So if you want to dig that next level deeper and really understand the data behind this and the thinking behind these prompt engineering techniques. And to some extent, a lot of times what you'll find is these papers will look at these prompt engineering techniques and how they work with different kinds of data sets on different kinds of language models. So you might even get a little bit of an insight reading some of these papers about the model that you're using and how it responds to different techniques like this. So I like having access to all the academic research. And there's also a lot of access to prompts themselves and in some cases to source code. So I feel like this is a really complete resource that takes you through both conceptual and gives you access to the deeper dive. So big fan of this resource. So I'll just go through a few prompt engineering techniques. There are lots of them. This is, like I said, a whole field of study. One of them is system prompts, which is the notion that you give the language model a role as the system. So you might say system : you are a helpful AI agent that answers questions in this way, or Give it whatever sort of guidance that you want, and then you give it as the separate role, you give it the input supplied by the user. So you might say user colon, and then whatever the user typed in as the question. So they have the system prompt gives us some context about how to answer the question. And that's a super effective technique. There are one-shot and few-shot learning. So generally with sort of zero-shot learning, it's you can rely on the language model to know how to solve a problem, to understand the kind of logic to apply. With one-shot learning, you're going to give it sort of a data pair. It could be an input and output. It could be a sample and a response. You're going to give it a model so that it understands how to answer the question. And if these are formatted correctly, they can be extremely powerful. Like a one-shot can actually radically improve the accuracy of a lot of prompts. And then in some cases, few-shot learning actually, where you're giving it several examples, typically not more than a handful, can also, in certain cases, give you big increases. There's chain of thought prompting. This one I think is super interesting. That if you tell the language model to solve the problem step by step, to break it down step by step, and literally you can just say the word thinking step by step, 4 words. You can put that into your prompt, and that will cause most models to appear to be a lot more contemplative about the process and to be much more accurate in the response. So if you just sort of say, "Hey, solve some problem," sometimes you get a very abstract, high level sort of shot in the dark answer. And if you say that same thing, except thinking step by step, you will very often get, okay, well, here are the steps to solve this problem. I have to figure out this, and then that, and then that. And then as it does that and computes the result at each stage, all of a sudden you notice that the summary answer you get at the end is correct. So chain of thought prompting, and there's tree of thought. There's a whole bunch of variations of this, but it's super useful. There's iterative refinement and prompt decomposition or prompt chaining, and there's a technique called REACT, which is reasoning action pairs. But they're all sort of variations of this idea that we're going to break the problem down and we're going to let the LLM solve it one step at a time. So there's a prompt decomposition Medium article that I think is really good by this guy named Justin Mueller, who's works at AWS and has helped many customers implement prompts to solve their LLM problems. And he goes through a pretty good description of some accessible prompts that are broken out and kind of why breaking them out makes sense, and even to the point of showing how how the latency and the accuracy and the cost are all generally positively improved by breaking the prompts down. And I'm not going to go into too many of the examples, but I guess just to give you the general idea, sometimes you have to inject a lot of information into the prompt and the prompt is fairly complex in terms of what it asks the language model to do. So you have a complex prompt that requires a lot of context to be able to solve the problem. And sometimes breaking those things into pieces means that each individual logic step is much simpler and has a much higher chance of success. And the amount of data required to drive that decision is also much smaller. So that's why you can make the overall performance actually less expensive and faster. And more accurate by breaking these prompts into pieces. And one of the examples he goes into, which I think is a pretty good one, is the notion of trying to find a summer camp for kids where you're giving the availability of the child, their age, and their interests. And in the model where you do that in a single pass, the LLM basically needs access to all of the data about all the summer camps. And it has to make a fairly complicated, weighted sort of decision about which ones to suggest. Whereas if you start breaking that into pieces and say, okay, I have a child that's this age and this is their availability, which summer camps are available, you get back a short list. And the only information it needs to solve that problem is what are the summer camps, what ages do they take, what dates are they available. And then you say, okay, great, given these summer camps that are available that fit those criteria, which one matches their interest better? And now you can have some deeper information about that smaller set of camps and make a more specific recommendation based on matching up interests. So that's the one example that he gives. It breaks it into, I think, 3 prompts: smaller, faster, cheaper, better. So there are definitely some good opportunities to break these prompts up and make them work better. It's pretty prompt and domain specific. The other example of that is structured decomposition, which is a paper that just came out like very recently, within the last month, from National Taiwan University. And what they found is that when asking the LLM to produce structured output, to say produce this output in JSON, for example, and when they were very specific about the form of the JSON they wanted, that in some circumstances the performance of the language model was dramatically worse. And so they tested a few variations against some standard benchmarks, And the variations were essentially natural language. There was a natural language which in 2 passes where they would essentially say, give me the answer in natural language, and then they would chain that and say, now convert that answer into JSON. There's one where they just said, can I have the answer in JSON? And then one where they said, I want the answer in this very specific JSON form. And so what they found, and I'm not going to go into the details of this, but just as an example, so here are 3 of the benchmarks that they use. These are the reasoning benchmarks. And then for each one of these, they show the natural language, the 2-pass where they do the natural language and then format it, the looser JSON, and then the specific JSON. And then they show several different models. So the Gemini 1.5 Flash is what I'm using. And what I can see, which I've noticed when actually using this model, is that natural language text, excellent result. 2-pass, excellent result. Loosely formatted JSON sort of varies. It could be anywhere from pretty good to pretty bad. And then the specific JSON is almost always very bad. Like it's significantly worse. So this is a case where if you're solving a problem like this, and this is the problem that we had, you're going to be much, much better off breaking this prompt into 2 pieces and chaining them together. So saying, hey, go solve this problem, answer this question, just give it back to me in natural language. And then I'm going to feed that natural language back in and say, convert this to this JSON format. And if I do that, I'm going to get these results here, which are essentially equal to the natural language. Whereas if I try to use the structured generation, I'm going to get way, way worse results. And then again, if you look at how it works on, like, say, classification, for example, I'm not going to go into it, but almost no difference. It really makes very little difference on the classification model. So this is, again, a case of understanding what model am I using and how does it perform in the kind of action that I'm asking it to do, and what can I do to make that better. And I guess that's maybe when you start getting into the engineering and prompt engineering. So there's retrieval augmented generation as another prompt engineering technique, which covers a sort of a variety of techniques of going out and getting data related to the problem you're trying to solve in the prompt, and it's supplying that data to the prompt so that it has some reference data and isn't just relying on the model. And then automatic reasoning and tool use, which I'll talk a little bit about in a minute, is kind of a new emergent behavior that we've seen where we can give the LLM access to tools and it will use those tools in its reasoning. So we'll talk about LLM grounding. Grounding is really any technique that's used to provide the model with true information and to tether its output to that information. So this is a way to combat the bullshit problem if you do it right. And it also allows the LLMs to process your own data, your own private data related specifically to the customer or to your problem domain, data that's owned by your company that isn't public, for example, and to reference that data and build answers based on that data. So instead of building answers based on the model. And particularly lately with the current models and sort of the current prompt engineering techniques, in many cases, it's more effective to use grounding than it is to try to pre-train or fine-tune a model on your own data. There are some examples, I think, exceptions, which I think if you're trying to train skills, there's still cases where it makes sense to do that kind of fine-tuning. But if you're trying to build a model that understands how to navigate your own data and give you answers in the context of your own data, that grounding is really the way to do that. There are a variety of techniques that fall under grounding, but retrieval augmented generation, or RAG, is really the most common one that covers most of what people do with grounding, and we're going to talk about that. So retrieval augmented generation is anytime you're going to go out and get external data and inject that data into the prompt. And typically it's going to be relevant to the context of the prompt itself and the problem that you're trying to solve with the prompt. And I've broken it in this is just sort of my own personal classification, but into kind of 2 modes. The one that I call static context retrieval, where we're going to take we might use the context of the user within the application, what they're doing in the application, as part of the process of determining what data the prompt needs. But we're not going to take a question that the user typed, for example. This is not like a chat type of a situation where we've got to figure out what the user wants. This is a situation where we know what the user wants, and all we have to do is go get it and inject that into the prompt. And so I'll give one example, which is if you were going to build a service that allowed the user to explore the Declaration of Independence, to ask questions about it and to get references back to it with specific quotes from that document, you could just inject the Declaration of Independence into the prompt along with whatever question the user asked and have the prompt give you back references to the Declaration of Independence. So you would have something that's grounded in the actual document. All the references would be references to the actual document. There's no hallucination. That's a pretty straightforward example. And then we have dynamic context retrieval, where we're going to take the question that the user has asked. We're going to try to assess what's relevant about that, what's semantically important. We're going to go try to find some documents or some segments of documents that are related to what the user wants to know about. We're going to pass those to the language model and ask it to figure out the ones that are relevant and give us an answer back based on those. So the example I give there is, let's say that you wanted to know about any bills passed by the 117th Congress that have to do with fracking. So you might ask a question about fracking, and what the software would do is say, okay, I've sort of assessed that the question is about fracking, so I'm going to generate a vector, an embedding that has to do with fracking, and I'm going to search this giant database using some semantic search techniques, different kinds of machine language or machine learning techniques, to go find a bunch of relevant documents or sections of documents related to fracking. And then I'm going to return all those documents, which are going to be injected into the prompt, and then the prompt will be able to evaluate that small set of data. And I would have said it wouldn't be practical to just stick the 7,000 pages of bills that were passed by that Congress into the language, into the context. Although with some of these 2 million token contexts, you probably could do that. But let's just say, for the sake of argument, that's generally not what you want. You want to answer questions about fracking. You can just go grab the snippets of those documents that have to do with fracking. And then another example of dynamic context retrieval is Google grounding via Google search. So this is something they do with the Gemini end user product, and something you can do via API if you want. You can also have it connected to a Google vector index, but essentially Google will take your question, and it'll do the same sort of thing. It'll figure out what the question is semantically about. It will do a Google search that produces some set of documents, and it will give those Google search results to the language model as part of the prompt, and tell the language model to answer the question in the context of those documents that it gave back. So it will ground the answer in its own search results. And that seems to sort of work okay. And it also gives you back, especially if you're Google and you're trying to promote Gemini and Google search, it gives you back documents that you can then go dig more deeply into, that are the documents that inform the answer that you got. So another example of kind of dynamic context retrieval grounding using retrieval augmented generation. So let's dig into how we use LLMs at TeamSpark. First of all, we'll talk about the tooling. We use the Gemini models, the text chat models, sort of the normal generative AI models. We use image processing. These are a separate set of machine learning models that are able to process images and turn them into text, extract text out of it. That's still considered generative. We use the prediction APIs. I think they're sort of poorly named, but these are APIs that generate embeddings and are able to sort of understand the context of the embedding. So whether the embedding is from a question or from a document or from other sources. So they're able to generate these vector embeddings that we can use for semantic search. And then we use vector indexing and search on Cloud Firestore to take those embeddings, convert them to vectors, and then to be able to do semantic search against our Cloud Firestore database. And I'm going to show you an example of how we actually do that in code in a little bit. And then let me show you quickly the model playground for Vertex AI, because it was an inspiration for some of the work that we did. So here's the Google Cloud Vertex AI dashboard. I'm in the language part of the AI Studio, and I have this interface where I can type a system prompt. I can type an actual prompt. I can see how many tokens that is. I can run the prompt and get a response, see how long it takes to execute. And then over here, I have the configuration. So I have the model that I'm using, the region I'm in, the model parameters like the temperature and the output limit. I can have whether I want to ground it and how, stop sequences. I can set safety settings. So these are sort of all the things that you can set, and then I have some advanced like top P and top K. So these are all of the settings that determine how this prompt is applied and how the prompt operates. So for sort of free-form exploration of how the Gemini engine does in response to specific prompts, this works fine, and you can do a little bit of exploration around prompt techniques and sort of what works and what doesn't work. And they do have the ability to save these, so you can save templates and kind of go tweak those. But it still doesn't quite get us where we need to get to if we're really trying to figure out how to, at scale and in context, figure out how to engineer our own prompts to solve some of the more specific problems that we're solving in our application. So it's a great way to get introduced to what it can do, maybe do some basic validation of prompt techniques up front. But when you start getting into the nuts and bolts, it doesn't quite get you where you need to get to. All right, so let's talk about how we use it. I'll show you the docs in a second, but we have two real use cases right now that are in the product. One is question answering. So this is the ability for you to just sort of ask a question of the TeamSpark app at any point in the app, to ask it questions about your timeline, about messages, posts, comments, whatever you want. And the other one is summarization. So summarization of posts, comments, channels, messages, messages in a channel, all the channels. So sort of anything that you might want to get a summarization of without digging into the details of, we can summarize for you. I mean, we do that in slightly different ways depending on what the thing is that we're summarizing. And in all these use cases, we'll have converted any media, any images or video into text captions. So we do use the image to text LLM in addition to some of these other techniques, just to do sort of these basic question answering and summarizations. And in the future, I think we're thinking about sentiment analysis, about understanding things that are sort of more positive and more constructive, and how to elevate those in your feed, and also understanding network and connection relationship analysis to understand how people are connected to each other in a way to, again, try to sort of build the feed that works better for you. And these will all be things you can opt in or out of. We're not going to like force an algorithm down anybody's throat, but we do think there are ways to improve the user experience with some of these more advanced techniques. So we'll go to the API docs. This is if you've seen any of the previous podcasts, this is our open API, public API spec. We're really big on having a public client API, so that if you don't want to use our client, if you want to build your own applications or write your own client, you're free to do that. So these are all of our APIs, well documented and testable within this interface. And these are our GenAI APIs. So this one is what we use to generate embeddings. That will probably move to the admin APIs because the clients don't have any need to do this. That's just sort of part of how we do our search. But the rest of these are all things that the client calls and that end users can call. So if we go into an example of, let's say we do this AI question RAG. So this is a question answerer that uses retrieval augmented generation. And so you can see it'll take the group ID that it wants to ask the question about. And then in this case, the question is any good cat pics. So let me just run this API. I probably should have put in the properties of LLMs so that they can be sort of slow relative to other operations. So, when we're doing big data stuff, we're expecting response times in the single digit milliseconds. And these things can be, here's a case of almost 10 seconds to run that thing. So, and then I got a response back. Yes, there's one post with the ID post 2. It's a picture of a cat with the caption, when your cat gets the PagerDuty before you do. So I'll go into like how we executed this, but this is what the API looks like. You're going to get a response text. You're going to get the prompt version, just the prompt ID and the version number that was used to generate it, and the token count that you spent to generate that prompt. So pretty straightforward. Not a lot of parameters, a lot of complexity for the end user version of these APIs. So let's talk about how we do the question answering. We use these ML text models to index and semantically search text via text embedding vectors. So if you look at the diagram on the right, you'll see this 3D semantic feature space where we have this three-dimensional matrix of gender, royalty, and age. And if you look at how it works, you sort of have gender where it tends to female on one end and male on the other. You have royalty where it tends from non-royal to royal, and you have age, which is young to old. And you can see things like someone who is male and royal and older corresponds with king, and someone who is not royal and younger and male is boy. And so one of the things we can do with this is we can determine the semantic distance, the similarity or difference between two terms by looking at the vector in between the two terms in this 3D matrix, which is interesting. And the other thing we can do is we can actually understand the relationship of these things to each other by manipulating the vector. So for example, if you took the vector for king and you subtracted the vector for man and you added the vector for woman, it would result to queen. So you can actually sort of compute how these things relate to each other, which is kind of clever. So this is a very, very simple example of 3 dimensions, and an example where the features are things that you understand, things like age and gender and royalty. What happens in the real world is these models are trained on massive amounts of data, that the features are extracted by the models through just a huge amount of trial and error, billions and billions of iterations of different tweaks and turns to try to come up with the right things that predict the relationships the best. So oftentimes you're going to have these hyperdimensional vector embeddings. So you're going to have, in our case, a pretty common case is 768 vectors. 768 dimensions in these vectors, and those dimensions aren't really going to correlate to anything that you would understand as a person. So it's sort of like while you can visualize this 3-dimensional, semantic features, the 768 dimensional automatically determined features it kind of boggles the mind. The other thing to think about is when you go from 3 dimensions to 768, it's not 256 times more. It's it's 2 to the third versus 2 to the 768th. It's exponentially, obscenely more complex. And these vectors are 4 bytes each. These dimensional vectors are 4 bytes each, which means you have about 3K bytes worth of data to represent the meaning, the semantic meaning of a given word. And the way that we use those is Cloud Firestore, and actually many databases support this. They support this notion of vector fields or vector indexes, and search mechanisms that can essentially sort these vectors by their closeness to a given vector, either using next nearest neighbor or cosine or other mechanisms determining the distance between a target vector and the vectors in the data set. So I can take a semantic vector and find things in my data set that are closely related to that. So what happens is when we create or update a post or a comment or a message, one of the first things we do is we see if any media has changed, any images or videos, and if so, we generate captions for those. So we have text that represents them. And then we take that text along with the text of the post, comment, or message, and we chunk it up. So we'll divide it into sentences. We might divide it even smaller than that. We might remove certain kinds of phrasings. We might remove certain kinds of punctuation. And we'll come up with what we think are the kind of semantically meaningful chunks of text that come out of these texts and images. And then we'll generate an embedding for each one of those text chunks, and then we'll store each one of those text chunks with its embedding and some information about the text chunk. We'll store the actual text itself, the type of the text, the kind of record it came from, and the vector in this big index. And generally, you're going to have multiple embeddings per record. So if you have 3 or 4 sentences of text and an image, it maybe results into a couple more sentences. And then by the time you chunk that up, you might have 6 or 8 or 10 of these vector index entries that are going to represent the semantic meanings of the things that are in those images or posts. And then when the user asks a question, we go through a sort of a similar process where we take the question, we do a little bit of text processing to come up with the semantically meaningful chunk. In this case, we're going to generate a single chunk, regardless of how long the question is, because we're trying to find something that's semantically related to that, whatever the user asked. And then we're going to perform a vector search against our embeddings collection. So we're going to go perform a vector search to find the nearest matches semantically, the nearest matches in meaning to the thing that the user is asking about. And then we're going to pull all those records together, and they can be different. They can be from posts, comments, messages. They could be text or media. There could be a whole variety of things. So we're going to pull all that data together. Not all of it, but we're going to probably take maybe the 20 closest matches, and we're going to give that to the prompt as context and let the prompt go through and sort out what are the actual best answers to the question based on that data. So what happens when you do these semantic searches, it's kind of impressive if you look at the actual data based on what you search and it's kind of what you get back. Because if you have things that match it very closely, they'll typically be at the top of the list or very close to the top of the list. But even things that don't really match are in an order that kind of makes sense in terms of how related it is to this thing that maybe it doesn't match at all. But if, let's say that I do some semantic search, I can't guarantee that if I get 20 responses that the top 3 are going to be the 3 best. But I can pretty much guarantee that the top 3 to 5 are going to be in the top 20 somewhere. So because it's not an exact science. It's very rough. So you need to figure out how many hits do I want to go get. In our case, it tends to be either 10 or 20. And then we're going to give all of those to the language model. The language model is actually going to go through and look at all those things that it's going to figure out, oh, hey, this person's asking about cats, pictures. So I sort of know what that is, and I can look at these individual posts and comments, and I can figure out which ones are about cat pictures, and it can actually add a little bit of value in terms of filtering that out and prioritizing that properly. And I did the demo for that already, so I'm not going to do that now where I did any good cat picks. And summarization is the other one, which is done a little bit differently. So in summarization, what we're going to do is we're going to collect some general context. So we're going to get the person ID of the person who's asking the question. We might get the current date and time if we want to understand like how fresh the answers are that we're going to give them back. And then we'll go figure out, based on the context of where they are in the app and what they're doing, what we need to go get to summarize for them. So that might be posts or comments or messages. We'll grab the people that are involved in those posts, comments, and messages. So that might be people that are the people who made the post, the people who are mentioned in the post, people that you follow that made posts, things like that. And then we'll kind of do a little massaging of that, and we'll hand all that data into the prompt, which will go then do the summarization. And I can give a quick example of summarization through the API. So let's say I wanted to summarize a channel. So let's say in group 1, I happen to know there's a channel that's cleverly named channel 1. And this is in Markdown, so it's a little bit hard to read here, but this is going to give me a summary of the messages in channel 1. Just sort of take my word for it that that's reasonable. These prompts all need a little bit of work, which is part of the reason that we built all the stuff that we built that I'm showing you now. We still haven't quite figured out the actual prompts that we're going to use. So I really think I have a lot of hope for the future of art, of this automatic reasoning and tool use. And the general idea there is you're going to provide the LLM with functions it can use. You're going to give them literally open API specs that express here's the name of the function, here are the parameters it can take, here's the description of what each parameter does, here's the description of what the function does, here's what the return value looks like, here's what all those things mean. And in cases where it works pretty impressively. So the general idea is that the LLM now has this set of tools, and when it does this apparent reasoning, it can figure out how to use those tools to progress step by step through a problem. So it's kind of like the chain of thought prompt engineering, except it understands what tools it has and it can use the tools itself. So, and so these tend to be multi-turn, although they can be serial or parallel, meaning it might invoke several tools in one turn and say, like, I need, go answer these 3 questions for me, or it might give them to you one at a time. But you're going to go through multiple turns, just like you would if you were doing prompt chaining or one of those other techniques. And I think, the way that I look at it is if you thought about the summer camp example of breaking that prompt down, for example, I think with tool use, when it's really done well, it can do that sort of thing for you, right? It could understand, oh, hey, I need to figure out what camps are available to take this age group. Oh, it's this set of camps. Now I need to go figure out what specialties and interests they support and go do that. And essentially do the same thing we did with all that by hand prompt engineering by just using the tools. So I'm a huge fan just conceptually that this will be a way to replace a lot of RAG, particularly for things like summarization and question answering, as the support gets better. The problem is it's not very good right now. The Google Vertex API implementation of functions is badly broken, in my opinion. It's probably not unrelated to the structure generation paper that I referenced earlier, where the Gemini model does pretty poorly when you give it a lot of structure, and function calling is sort of a very, very extreme example of giving it structure, because you're essentially saying you can only respond in exactly this way to this format. So I'm hopeful that Google will both understand that it's broken and care that it's broken and fix it. Or maybe I'll use a different model where it works better. So I'm not using this now. We have built some of this stuff and tested it. But I have a lot of hope for the future that this is really going to be the way we're going to do a lot of this RAG stuff, is instead of having to go break these prompts down ourselves and figure out all these steps, we're going to be able to have the language models use tools in a supervised way that'll be able to solve those problems more efficiently for us and be able to solve a wider variety of them with the same set of tools. So let's talk about prompts as code. Prompts as code is a term that I think I made up, and I'll kind of get into why that is. So let's first talk about what is a prompt. So a prompt is the text string that you send to the LLM. So here's an example of one of our actual prompts. It's a system prompt that says you are a helpful agent. Given this message, summarize the comments from the perspective of the user with this ID. And you see inside of the brackets, we have some tokens that are going to get expanded out. So those are called placeholders. We'll talk about those a little bit more later. That's a fairly common technique, that when you're going to inject data into a prompt, that you use this placeholder notation. But that's not all the prompt is. The prompt is really anything that influences how the prompt is evaluated by the model, including the version of the model itself. So what model I'm using, what version of the model, any generation or safety parameters for that model, turn limits if I'm going to have multi-turn prompts, like anything that influences how that prompt works is part of the prompt by our definition. So if you're going to think about how I'm going to version control or how I'm going to generally manage prompts, it's not just the text string, it's all of the things that make up the prompt and how it's evaluated. So is a prompt content or code? And you probably already know where I come down on this. There is a camp that says the prompts are content. And it's probably the consensus view. They manage prompts as content either in CMSs or in CMS type systems. So they view changing a prompt like they would view changing the text on the homepage. Like this is something that engineering doesn't do. This is something that marketing does or somebody else does that's independent of the operation of the site. And they view prompts the same way. They may have a specialization of prompt engineers who are separate from the engineering team, who are building and testing and deploying these prompts and A/B testing them and doing all kinds of stuff, just like you would do with content. And I can sort of understand it. Like I'm not convinced that that's wrong, and I could definitely be convinced that for a certain kind of product and a certain kind of team structure, maybe that's the right way to do it. Particularly if your CI/CD hygiene is not great, if you can't push stable releases at will frequently, or if you don't do that, I can see how this would be a better way to do it. And you probably already know how I come down on this, which is prompts are code, like configuration is code, like secrets are code, like code is code, like infrastructure is code, like everything is code. Everything is code. Everything goes through the same CI/CD process, the same review process, the same test and validation process. It's deployed the same way. It's rolled back the same way. So my opinion really is that the prompts are code, and we should treat them like code. And at least in our application, with a single engineer writing prompts and writing code, it's definitely the right way to go. So what are those prompts that are code? So I look at it as you have the prompt itself, the framing device. So that's has an ID, has a description, has notes, which are generally aimed at the prompt author to explain how the prompt operates and what context it has and what placeholders it will have. In our case, we have a one-to-one relationship between prompts and API endpoints that use those prompts. So the prompt includes the API endpoint. We have a collection of prompt versions, which are really the meat of what the prompt that actually gets executed is. And then we have a live prompt version, which indicates which of those prompt versions is the one that we're actually using in production right now. And then the prompt version, it has a version number that monotonically increases. It can have an optional label. It has the prompt text, obviously. You can have description and notes for your own internal record keeping, and then you have the model used, all the model parameters, the configuration safety parameters, and the turn limit, and there may be other things that end up in the prompt version over time. Once that prompt version is committed, it's immutable, meaning that you can once version number 1 is committed to source control and deployed, that can never change. So the nice thing about that is that if I record what prompt was used, the ID and version number of a prompt that was used in a log, for example, I can go back at any time historically, find a prompt that was used, and go look in the version controller in the source code and see what that prompt was exactly, not just the text of the prompt, but all of the attributes of that prompt. So once committed, they're immutable. The way we execute the prompts is we have a prompt state. So this is an object that we create that has the placeholders. So these are all the key value pairs that are going to be replaced in the prompt itself. So all the things that we inject into the prompt, things that are part of our RAG implementation. Any functions that the prompt uses, if we're doing function usage by the prompt. So that's going to be the definitions of the functions in OpenAPI format, and also callable implementations, typically with a closure around it. So you have the right context to be able to call those functions on behalf of the user and the context that they're in. And then any media that the prompt uses. So the prompts can process media, they can process images or videos. So you can give it an HTTPS or a direct Google reference to one of those files. And then we actually call a single function to generate our response from our prompt and our state. And that covers every use case. That covers RAG with injection, with placeholders, media payloads, function use, multi-turn, any way that you can execute a prompt to generate a response is going to call a single function that's generate content from prompt version, which is going to take a prompt version and prompt state. So we can switch models and parameters and modes of use all through the data that's in the prompt version of the prompt state, calling this one single function. All right, so let's talk about our prompt engineering APIs and the tooling that we've built around them. So all of our GenAI APIs, that's a little mouthful, they sort of require code that runs against our data to establish the context that we use for generation. And so that's a mouthful, but let's just give an example. So when I say I want to summarize the contents of a message, that means we have to go get a message. So we're going to access it on behalf of a tenant and a user. We're going to get a message maybe from our mock data that's realistic and that's in our mock tenant. Then we're going to have to do some processing of that. So we're going to take that data that we get from the database and we might massage it a little bit. We might augment it. We might remove some things. We might tweak the formatting a little bit. And then we're going to make that data available to the prompt. But that whole process is sort of part of what makes up the environment that the prompt executes in. So you could argue, well, you could just extract that data as text and build some library of that data and use, some more traditional prompt execution, use the Vertex API playground or something, which maybe you could do. But then the problem is if you change the schema, if you change any of the logic for extracting the data, anything else in that flow, then you've sort of broken that connection. So you're back to like this problem of like, well, now I have mock data that I have to maintain somehow separately as I change the underlying data structures and the way the code works. Just doesn't seem manageable. So Vertex AI Studio is great, but we need something that works with our APIs in our context. And we really want a high degree of fidelity to production. So we want it to work just like the app works, as close to the way the app works as possible, so that when we're doing our prompt engineering, we can really see how it works against real data, the way the app's going to use it. So let's talk about how we do it in the code. So we have prompts and prompt versions in code. So the prompts and prompt versions are defined in the module that uses them. So in the API endpoint implementation that uses the prompt is where the prompt is defined, and then we register the prompt when we create it. So I'll give you an example. So this is an endpoint. This is a question answering endpoint. Summarization, sorry, providing a summary of it's summarized posts. So in the top of this, so this is the actual get endpoint that summarizes the post. So on the top of this module, we're going to create a constant all caps prompt. This is the same in every one of these, just for consistency. And then we're going to create a prompt object, which has the ID. So in this case, it's summarize-posts, which kind of correlates to the API endpoint. We're going to have a description. We're going to have notes, and these are notes for the prompt version author. And among other things, you're going to tell them what placeholders they have access to, what context we're going to create for them. It has the endpoint. We're going to process that automatically and build a relative endpoint from the endpoint itself. We're going to have a set of prompt versions, and then we're going to have an indicator of which version the live version is. So in this case, there's only one, so the live version is 1. And then we're going to create the prompt versions underneath that. So here's the actual prompt string that we're going to use, the version, some notes, what model we're going to use, Gemini 1.0 Pro, and then generation config. We're going to set the max output tokens. So this is the prompt, and then we call register prompt wrapped around that whole thing, which will register all the prompts for all the endpoints in a static prompt registry that we can then use from our APIs to interrogate what prompts are available in the system and to actually test those prompts. So as I said, we have a prompt registry that keeps track of all those registered prompts. And then we have some prompt management APIs. So I'll give you a brief view of what that looks like. So this is our API, our admin APIs. These are only available if you are an admin user, which means basically a developer at TeamSpark. So I have the ability to interrogate the set of prompts that I have in the system that are registered and to get the details on any given prompt. So that's sort of all there is to that. And then the prompt execution API design. So for each one of these endpoints, we basically have an end user endpoint that's API/AI/name of the endpoint. And we have an admin version of that same endpoint that can only be called by the admin role. That's /admin tacked onto the end. So for the user entry point, this is just basically what the client application calls. So it uses the live prompt version that's configured. It's called in the context of the current logged in user, and it returns a summary of results. So really basic, just the text, the prompt version string, and the token count. Pretty straightforward. The admin entry point, you can use any prompt version that's registered, and you can even give it an entire prompt definition base64 encoded. So you can test any prompt combination that you want. You can use any user context that you want. You can override your current user or the default validation user. So you can do this in the context of any user. And the results you get back are quite a bit more detailed. So you get back the same summary results over here, but you also get back the execution state. So everything that we build in the state that we passed into the execution, you get back. And then the detailed generation results that you get back from Vertex AI, which are like hyper detailed. So you have the ability to do a lot of investigation kind of debugging when you use the admin API endpoints. And I'll show you why that is important in a second. So if we go back to look at the code for this, if we look at the implementation, it's pretty straightforward. So basically every one of these endpoints starts with this block of code. So we're gonna first see, are we calling the admin user, and if are we calling the admin path, and if so, are we an admin user? So we're basically saying is admin. So is there a /admin at the end of the path? And if there is, are we an admin user? So we're going to get a Boolean for whether we're admin. Then we're going to get the prompt version. This is not the prompt version ID, but the actual whole prompt version object. So if we're not an admin user, it's just going to get us the one that's the live version. And if we are an admin user, it's going to see if we've overridden that with the prompt version or an entire base64 encoded prompt. But either way, it's going to return the prompt version that the generation function is going to use. the prompt version object, and then we're going to find out what action user we are. So if we are not an admin user, it's just going to be us, and if we are an admin user, we may have overridden the action user. So is admin, prompt version, and action user are determined for every API endpoint. That's kind of the admin front end. Then the rest of the logic is exactly the same. So whether we call it as an end user or an admin, this chunk of logic is all exactly the same. So in this case, for this summary case, we're going to get the group ID. We're going to go get the posts for that group ID. This will get us the last 10. We're going to get all the people that are related to that post, anybody mentioned, the person who posted it and anybody mentioned in those posts. Then we're going to make that a unique list. Then we're going to go get those people. And then we're going to build the timeline context that we pass in the prompt, which is the collection of posted people. And then we're going to go execute it. So first we're going to create the prompt state, which is going to have a set of placeholders. So we have the timeline and the person ID are the placeholders, which are the ones we defined up here in our notes. And then we're going to go call that single entry point for generating content, generate content from prompt version. So we pass in the prompt version, which again is the whole prompt version object, and the prompt state, which is this thing. And that's going to create a summary. That's going to create a response, and we're going to pull the summary out of that response. So if we're not admin, we're just going to return that summary. And if we are admin, we're going to return all these details in addition to the summary. So this is sort of the tail part of the thing we do on every one of these entry points to handle the admin side of it. So the middle part is exactly the same whether you're admin or not admin. And there's a little bit up front and behind that's pretty copy-paste if you are admin that handles that other use case. So why do we need to build all this? It's probably the question you're asking yourself. What's it for? So we built TeamSpark Prompt Studio, and that allows the prompts to be tested, tuned, and validated in the context of the APIs that use them. It leverages the state creation of APIs and realistic data. And I've sort of talked a lot about why I think that realistic test data is super important and why not mocking things is super important. And so this is an example of we don't have to mock anything. We're going to call against the production database. We're going to call production-like data, and we're going to run the actual application logic that creates the context that the prompt operates in while we're tuning and engineering that prompt. So let's give you an example of what that looks like. So this is our TeamSpark Prompt Studio. So we have links to the API documentation, and then we have a series of prompts. So this is our prompt registry. This is everything that got registered when their endpoints got registered. So we have question art, which is our question answering with tool usage. We have question rag, which is question answering with rag, and we have a bunch of summarization ones. So if we look at like question art, for example, we can see some notes about what it is, the endpoint that it corresponds to, and then we have a couple of prompt versions. So we have, this is an older version of the prompt, and this is a newer version of the prompt, and this is the live version here. So version 2 is live. So we can sort of see, yep, I got a prompt, and I've got a couple of versions I can run. Let's go look at one we can actually test. Let's go look at the rag question answering. So I only have one version here. So first of all, we go to look at the notes, and we see that this is essentially instructions for the prompt author. And among other things, it's telling them they're going to have a placeholder called context and a placeholder called question that they can use in the prompt. So we only have one version, which is the live version. And the prompt is using only the following likely relevant context with the placeholder, answer the following user question, and then user with question. And I'm using Gemini Flash 1.5, temperature of 1. So let's go select that. So now I can see what all the details of this prompt in sort of form style. So I can see the prompt version, the model, all the model parameters. And let's go test the endpoint. So if I want to test this prompt version at this endpoint, I'm going to add some data. This is the same stuff I would have passed if I called it from the OpenAPI document. So the way this works is essentially this is the same. This is just a form visualization of the prompt version, and this I actually interrogate the OpenAPI YAML file where the APIs are defined to figure out which parameters are allowed, what types they are, which ones are required. So this is all generated dynamically. This whole application is generated dynamically, basically. And let's say I want to test it, I want to run it 3 times. So it's pretty useful when you're doing prompt engineering to look at multiple prompt runs at the same time. So you can sort of see, because sometimes you get lucky and get a great answer. Sometimes you get unlucky and get a terrible answer. So if you get like 5 or 10 answers, it's kind of easy to see, hey, is this generally trending in the right direction? So I'm going to go run this prompt for the live prompt version with some parameters I passed in and just run it 3 times and see what it outputs. Okay, so I got 3 outputs. All sort of reasonable. And if I want to dig into the details of those, I can see, okay, here's my metadata, so I can see how long it took. It's actually pretty fast. This is the summary that I would have got back if I'd called it as a user. So I get the response text. There's the text. I get the prompt version, so question-rag:1, and the token count. Now I have the entire prompt version object broken out. So everything that we saw before up above. They have the prompt state. So this is everything that was generated by the code that implements this endpoint. So the placeholder, which has all this context, if you need to sort of see what that is, it's a little bit ugly, but the LLM can understand it. And it'll also have the current user ID and then the question that I asked. And then this is the actual detailed response that comes from the generation function from Vertex AI. So it's formatted in kind of its own special way. It's got its finish reason, all the safety ratings, a few other things. And then I've got some usage metadata at the end. So I can see the prompt token count, the candidate token count, which is the response, and then the total. So I can get really, if I really want to get into the details of why I got the answer I got and what data I provided, I can see that here. And let's take another example. Let's say, okay, we want to do a little prompt engineering, so we're going to edit this. And I'm going to just do a very simple one just for the sake of the demo. I'm going to go ahead and change the temperature of this model to 0. So the temperature ranges for this particular model, it ranges from 0 to 2, with 0 being essentially no variability, no randomness. I want complete predictability of output, and 2 being like go nuts. So 1's usually pretty good. 1, you'll get a little bit of variation of output. You'll get a little bit of creativity, a little bit of sort of personal feel, but not too crazy. But 0, in theory, and it doesn't work every time, but in theory, if it's 0, you should get the same exact answer every time you call this. So we're going to do the same thing again. I'm going to run this 3 times with this modified prompt. So that's the same answer 3 times. So that's exactly the same predictable answer 3 times in a row, which kind of shows that changing the temperature worked. And let's say, hey, I like that one, so I want to make that the new version. It's a little bit clunky, but I can go now view this prompt version as JSON, and I could copy this, and I could go into my code and I could paste this in as version 2. And if I want to make that the live version, I can make that the live version. So that's our Prompt Studio approach. And what it really allows you to do is to start being a little more clever with changing these prompt strings, running a bunch of outputs, comparing them to the old version of the prompt to see how they differ between the two to make sure you're going in the right direction. And you're doing all that by leveraging the actual code that's generating the context that you need to run these things in. And if you're changing those, you're going to be able to see that all as well. So if I go in here, like I'm in dev mode, and I'm like, you know what, the way that I'm building this context is not helping. I'm giving it too much data, or I'm not formatting things properly, or maybe I need to dereference some things to make it a little bit easier. So I start changing this code. I can test all that in one place. So I can test the building of the context and the execution of the prompt against that context in sort of one unified place that's using the actual production code and the production endpoints. So anyway, this is what I wanted. I think it was worth it. It was probably 2 weeks worth of work to do all of this, which I think, given the amount of time that we're going to be spending in prompt engineering and tweaking and tuning, and the fact that we want this to be a comfortable environment where people want to come work in it and they want to make the prompts better, and it's not scary and it's not ugly. I think there's tech debt, and sometimes the tech debt is the things that you didn't do. It's the tools you didn't build that that keeps people from doing the jobs you want them to do because it's scary or unpredictable or dangerous or hard to learn or whatever. So I think having these tools is I'm happy with the investment I made. I think it turned out great. So the way the CI/CD works, pretty straightforward. You probably can already guess when I want to go deploy a new prompt version. I just change the live version to point to the new one and deploy the code. And if I want to roll it back, I'd roll it back. I can also do automated testing and validation. So I can use, hang on, that one a little crazy. So I can test the GenAI endpoints just like I test any other endpoints. If I tune the temperature way down, I can do that really easily. If I want to leave the temperature up a little bit, I can use some NLP tools to make sure that I'm getting the right answer. So an example of that might be on the cat picks question. I know post 2 is going to be the answer. I don't know exactly how it's going to be formatted. I don't know how it's going to express that post 2 is the answer, but I know that post 2 is going to be the answer. So there are things I can look for in the answer that tell me that post 2 and only post 2 were the things that were referred to. So this allows me to actually write unit tests that are not subjective range-based unit tests. They're pass-fail unit tests like code unit tests are. And I can do that with all these endpoints. And because I have these admin APIs, I have a lot more flexibility in how I can test and instrument those endpoints. And the other thing that these APIs allow me to do, these admin APIs, is they allow me to do horizontal analysis. So I can essentially script these GenAI endpoints using the admin endpoints to test across a whole variety of data inputs and a whole variety of prompts, and sort of build a matrix and run tools against that to see how those prompts are all doing and how they change over time. And the fact that I have all these endpoints, these admin endpoints, is what allows me to do that. So I think that was also a good investment. So yeah, hopefully that's been interesting. I'm really happy with the TeamSpark studio, and it's been super helpful. And now I'm getting ready to go spend a week really diving into actually making these prompts do exactly what I want now that I have the tools to do it. So that's the end. I will say there's some end notes. These are the things that I link to in the document. I'll put these in the comments of the video. I think these papers are great, and these are great resources. So anyway, thanks a lot for tuning in. Talk soon.